Well, hi everyone, my name is Pamina Georgiou, and together with my colleagues Bernhard Gleis and Lara Kovac, I worked on trace logic for inductive loop reasoning. So to give you an overview of what that means, let's just jump right in with an example. What we're generally interested in is the verification of unbounded data structures. So let's look at an example. Here we have a little program that basically takes two arrays, and we want to copy elements from one array to the other, but only positive ones, so bigger or equal to 0. And what we want to verify in the end is that B is initialized only by positive elements and only by elements copied from A. So basically the two properties, P1 stating that B only has positive elements, P2 stating that for every element in B there exists an element in A. So to prove this, you usually need existentially or even alternatingly quantified loop invariance, and you need some sort of concept of induction over arbitrary program time points. You will see why later in the talk. So historically speaking, automated reasoning is mainly driven by SMT solvers. So there are different approaches, for example, based on model checking and horn clause verification, like spacer or Freck-Horn. With this approach, you usually can quantify for all properties quite well. So you could probably solve P1, but most likely not P2, because P2 contains a quantifier alternation. Then there are other approaches based on predicate transformers, and basically Hoare logic, such as Daphne, and this gives you, in the presence of loops, quite a limited automation, since we require loop invariants that depend on the program and on the property. So in this case, you could either solve both with expert knowledge or none of them, if you can find the right invariants. And then basically you can also do it yourself with an interactive theorem prover and come up with an encoding of the semantics and the proof itself. So our approach differs in the way that we want to actually use an automated theorem prover for the verification of such properties. So automated theorem provers are great in competitions, and they are also great in their expressivity, since we can use arbitrary first order quantification in semantics and also in the properties. And we can also use theories by now, but the thing is, they are quite limited in their use for software verification because they just have not been exploited that much in that realm. So there are no standard established first order program semantics, and there is no clear way of handling induction over loops in such a language. So our research question was basically, can we find some more expressive first order program semantics such that program specific loop invariants can be generalized, so that we can get a higher degree of automation. So what does that look like? Basically, we want to find suitable first order semantics that increase the expressiveness and that are easily extensible for different forms of input programs. This talk here is focused on array programs, but last year we already focused on hyperproperties such as non-interference and program equivalence, so basically security properties. But then we're also interested in other input programs. Then we need to find a way to express induction over loop iterations in the language, because to generalize in loop invariance, we need some sort of way of expressing induction over these loop iterations for program properties. So how can we do this such that they hold for a larger set of input problems? And they should also be extensible depending on what kind of input problems we're looking at. And then third, we want to leverage the first order theorem provers to discharge the so-created verification conditions. So our verification task basically now looks like this. We take an imperative program with the safety property expressed in SMT-lib. We use our rapid framework to produce the first order program semantics with explicit time points. That means we have a concept or a notion of program locations and loop iterations of a program in our semantics. Then we further equip this encoding with the so-called trace lemmas, which are our generalizations of the loop invariants needed that are automatically instantiated and needed to verify such properties. And then we use the vampire theorem properties to discharge. So here we are dealing with programs that contain arrays and loops mainly. We use this explicit time point reasoning, as you will see in a second, and we use and we do functional correctness proofs. So we assume termination at the moment. So let's look into trace logic and the semantics. So what is trace logic? Basically, it's an instance of full first order logic with equality. So we have uninterpreted functions, data types, and linear integer arithmetic. So for program values, we use the standard theory of integers. For loop iterations, we use the theory of natural numbers without any arithmetic. So we have the zero, successor, predecessor functions, and the less relation. And we do reasoning over time points. So we express induction directly in the language. So induction over a loop, that is. And that allows us basically to reason about properties of all loop iterations and to reason about the existence of certain loop iterations, with which we can then generalize loop invariants, as you will see in a second. So what do our semantics look like? So when I say time point, what I actually talk about is a sort that expresses time points in the following way. So we have, for example, locations such as L4, which is just a constant time point. So this would be the location at line 4. We use location L6, that is a function over one natural number. In this case, the first iteration of the loop. At the beginning of the loop. So this would be the time point right here in the beginning of the loop. And then we can also express the next iteration, so which would be the successor of 0. Then we have a special constant. Since we assume termination, we have a special constant for the last iteration, which would be the first iteration where the loop condition does not hold anymore. And then we can just quantify by generally saying for all iterations L6 at this iteration, and quantify over time points in that way. So for an arbitrary iteration, it. Then our program variables are basically functions over those time points. So for example, I would be a function of a time point to an integer. A is a constant array, so that means it's only parameterized by the array position, which here can be expressed as the value of I at the location in the first loop iteration, at the beginning of the first loop iteration. And then B is a non-constant array, so B is parameterized with the time point and the location, which can technically be parameterized and the position, which can theoretically be parameterized by a different time point. So we could also say that B at the time point L6 IT and then use the value of J at another time point. So for example, at the end of the loop. And then semantics are basically quantification over those iterations and equality. So for example, for I equals 0, we have I, the function I over the time point L4 equals 0. To say that, to express the incrementation in each loop iteration, we say for all iterations smaller than the last iteration, I in the successor iteration is I at the end of the loop in the current iteration plus 1. And the same for the statement for the assignment of A at position I to B at position J. We just say if the if condition is true, then we assign in that way. Now, how do we now automatically prove such problems? So we need some sort of loop invariant generalization to do this. So because the prover alone cannot handle it, so we need a way to handle the induction over such loops. And to that end, we automatically instantiate a set of sound lemmas for each program variable, basically. And this allows us to do inductive reasoning, and we call them trace lemmas. So basically, trace lemmas are valid formulas that are derivable from instances of the induction scheme. And they're a manually identified set of useful lemmas. So we did manually identify them. And they can include quantifier alternations. And they can specifically include quantification over loop iterations and variable values. And as far as we know, they cannot be automatically generated by any state-of-the-art techniques, as they do contain quite intricate quantify alternations. So let's go back to our running example. If we look at the two properties we saw in the beginning now, to express those in trace logic, we will basically parameterize the values of B and J, the program variables B and J, with the time point of the end of the computation. So basically, to express that B is bigger than 0 everywhere, we would just say B at the end of the computation is bigger than 0 and everywhere. And the bounds of the array are then between 0 and smaller than J at the end of the computation, since J basically gives us the length of the area B. And the same goes for the for all exists property P2. Okay, so let's look at what we need to do in order to prove P2. So basically, the proof idea in trace logic goes as follows. We take an arbitrary integer k between the bound 0 and j at the end of the computation. Now, what we need to find is the last iteration where j has the value of k. Why the last one? Because we know that in the next iteration, like if in the next iteration j has a higher value, then we know that at this last iteration j has been updated, which also means that this is the iteration where b at the b at this position was set for the first time to a value in a. Then moreover, we need to show that the position k will never be reached again. Otherwise, we could maybe overwrite at some point in the future, overwrite the value of b at this position. So we want to exclude that. This can happen. And then we need to show that bk doesn't get changed anywhere else either, so that bk remains unchanged until after this first assignment to AI. So how do we prove the first part? So how do we find this last iteration such that j has the value of this arbitrary k? To do this, we have the intermediate value theorem, which is one of our trace lemmas that basically expresses that for all integer values x, between, in this case, j at the beginning, j at the end of the loop, and given that j is dense, so that in every iteration j is either stays the same or is incremented by 1, there exists an iteration such that j in the next iteration is incremented, and this iteration is smaller than the last iteration, such that j has exactly this integer value. So this gives us exactly the iteration that we need to find the iteration where b is actually set to a value in a. Now, the next thing we want to exclude is that the position k will be reached again at some point in the computation. So what we need to exclude is that array traversal is repeated. To this end, we used the injectivity theorem, basically stating for two iterations, one smaller than the other, if j in the successor iteration of the first iteration, so the smaller one, is incremented, then we know that any other iteration cannot be the same iteration as the smaller one. So basically, this just excludes that that we can go back in time. So the next thing we need to do is that we need to show that bk remains unchanged after being set. So basically what we need to do is we need to apply induction from between two different iterations, namely the iteration that we found in the first, with the first lemma, to until the end of the computation. So this looks like the following. Basically, for any position in the array, and given two iterations, a left and a right bound, if we can say that stepwise from the left iteration to the next iteration, for all iterations in between the left and the right one, the value of b at a certain position remains the same, then we can, thanks to induction, also conclude that b in the left and the right bound are the same at this specific position p. And basically with that and the fact that from the semantics it already follows that b is set, that b at a position k is set to a value of a, we can conclude the proof of our second property, stating that for any value in b there exists a value in a. Now, you saw one proof, but we actually have benchmarks of 45 unique programs that we basically took from the svconf repository with a total of 103 tested properties. We had to adjust the input programs a little bit to our language, since we don't use any program transformations or other additions to express, for example, for all quantified properties, we don't need loop transformations and things like that. And we could actually, by only using those three lemmas that you just saw now, we could successfully solve 78, so more than 75% of our input problems. And just for some quick visualization, these are our benchmark results. Rapid minus and rapid, so rapid star would be the current version of rapid, and we compared it to rapid minus, which would be the last year's version of rapid. The thing that we which is not part of the results in this paper, but that have been substantially meaningful for software verification with automated theorem provers, were two other works that have been published in this year's CADE, that basically worked on the prover side of things. So here we're interested in the encoding and what it needs, what the prover technically needs, but then we also needed to make the prover more suitable for software verification benchmarks, and this is basically the comparison of that. So as you can see, we could solve our input problem, which would be the copy conditional or the copy positive, which we couldn't solve before. And then we can now solve other hard properties, such as the partition problems, that are all properties that contain quantifier alternations. So to sum up my talk, we propose first order axiomatic program semantics in trace logic, and we do verification of functional correctness with a superposition based automated theorem prover. And we can, by using this sort of trace lemma reasoning, apply bounded induction and also synthesize loop splits basically, and find specific loop iterations to that end. And the main advantages of the approach are the expressiveness, which is given by the explicit time points of the encoding that allow us to do this kind of reasoning. They are fully automatic. So the verification is fully automatic with the trace lemmas, because the trace lemmas are basically just instantiated for every program variable. And we don't need any other program specific loop invariants with this kind of reasoning. And even though it involves some manual work, the approach is very versatile, since we can apply the different properties to arbitrary loop bounds. So thank you for your attention.